Hi, this video is to help you out with phase change calculations where you're trying to figure out how much heat is involved with either melting or boiling or perhaps condensing or freezing of water. Now we're going to be dealing only with two different formulas. All right, either we use the latent heat of fusion, which is Q is equal to M delta H FUS, or the heat of vaporization, which is Q equals M times delta H VAP. Now this may look a little confusing, but it's actually quite simple. Delta H FUS is simply a constant for water, all right, and it's right down here. Latent heat of fusion for water is 334 joules per gram, whereas the latent heat of fusion, latent heat of vaporization for water is 2,260. Now, the only tricky part is knowing when to use which one. Well, the smaller number is used at lower temperatures. Just remember that. So at 0 degrees Celsius, when water either freezes or when ice melts, you're going to use the 334 number because that's fusion. Whereas at a high temperature, 100 degrees Celsius, that's when you're going to use the heat of vaporization. All right, that's the higher number at the higher temperature. So looking at a sample problem, we have right here, how much heat is needed to melt 19.5 grams of ice at 100 degrees. Now, the fact that it's at 100 degrees, that's not part of the calculation, but that's our clue that it's going to be heat of delta H VAP. All right, I just noticed that there's a mistake. It's supposed to be at 0 degrees. Sorry. The reason I know it's supposed to be at 0 degrees is because, it's melting. So that's 0 degrees Celsius. So that means it's going to be delta H FUS. It's melting, 0 degrees Celsius. That's going to use delta H FUS, which once again is 334 joules per gram. Sorry about that. So we simply take the formula Q equals M delta H FUS. The mass is 19.5, and we're going to multiply it by 334 joules per gram. And on my calculator, all right, we have 19.5 times 334 equals, I get 6,513. Well, we don't use this number for significant figures because that's a constant. Instead, we just used a 19.5. There are 3 digits there, so I want to keep the first 3 digits here. Also, since this number is greater than 1,000, for sure I have to put it in scientific notation. So I'm simply going to go 6.51 times 10 to the third, since the decimal moves 3 places over, and the units are going to be joules. Now, the second part of the question, is it positive or negative? Is delta H positive or negative? Remember, delta H is the change in enthalpy, or the change in total internal energy. Since heat is needed and it's melting, those are the clues that we use to say, hey, look, heat is going into the system. All right, it's an endothermic process, which means that delta H is going to be a positive change since heat is going in. Now, the second sample problem, how much heat is released when 48.3 grams of gaseous water condenses at 100 degrees? Well, since this is 100 degrees, that tells us that it needs to be delta H VAP, which is 2,260 joules per gram. Again, it's dealing with gaseous water, and it's condensing at 100 degrees. This is all telling us that it's the larger number for heat of vaporization. Q is simply M times delta H VAP, so that's 48.3 grams multiplied by 2,260 joules per gram. On my calculator, I go 48.3 times 2,260, and I get a big number. But again, 3 significant figures here means I need to round off after the third digit, so after the 9. And it needs to be in scientific notation since it's a big number. So the decimal is going to go after the 1. I'm going to get 1.09 times 10, and it moved 5 places to get there, times 10 to the 5th, and the units are joules. And finally, is it positive or negative delta H? Well, since heat is being released and it's condensing, those are the clues I need to let me know that heat is leaving the system, it's exothermic, and therefore it is going to be a delta H is going to be negative. I hope you found this useful. If you need more help, please come to a tutorial.